Today, it's my pleasure to introduce our speaker, Igor Sikora from Bilkent University, who will be telling us about ROC2 graded coefficients of C2-Eilenberg-MacLane spectra. Take it away.
Okay, thank you very much. So thank you for the invitation to give this talk on this seminar. Yes, so the title is already given. So let me actually tell you what is the goal of this talk. And the goal is that we will compute the homology of a point. So, well, a priori, you might assume that it is not very ambitious, but we will do this in the equivariant world. So you will see that, well, it is not so easy as it may sound. So let's start with some overview. So in the non-equivariant topology, of course, computing the singular homology of a point with coefficients in some abelian group or a ring R is pretty simple. So we have the dimension axiom, which is telling us that in the degree 0, what we have is our ring, our group of coefficients, and in other degrees, the groups are 0. However, it is not so easy in the equivariant world, and here is an example. So on the left-hand side, what we have is just non-equivariant homology of a point with coefficients in F2. So I depicted it on well, a real line, but of course it is graded over integers, and of course it is concentrated in the degree 0. However, on the right-hand side, what we have is a C2 equivariant homology of a point with a equivariant analog of the field with two elements. And as you can see, on the horizontal line, we have the same picture as in the non-equivariant homology, but if we leave the vertical line, there is plenty of dots appearing over here. So we cannot say anymore that the homology is concentrated in degree 0, and it occurs that this homology actually needs to be computed. So the goal of this talk will be to describe a method for the computations of C2 equivariant homology of a point. So here is some heuristic. So we would like this method to make these computations feasible, and also to allow to unveil as much structure as possible. So our object of study, which we'll be discussing, is C2 equivariant homology, ordinary homology of a point. But instead, we'll be thinking about it as coefficients of C2 equivariant Eilenberg-MacLane spectra. And the method which we will use is the Tate method as developed by Greenlees and May. But before going to actual discussion, we would, of course, discuss why do we care at all. So firstly, equivariant homotopy theory, and in particular, equivariant computations, has proven to be useful in recent years in the whole area of algebraic topology. So the most famous example of this usefulness is the solution to the Kerber invariant. Oh, there is a word missing. So this is Kerber invariant 1 problem, where the solution was given by Hill, Hopkins, and Ravenel in 2016. Other application of a C2 equivariant stable homotopy theory is via the realization functor. It is connected to motivic homotopy theory. So there is a close connections between these two areas. Also, we have some applications in algebraic K theory, chromatic homotopy theory, and other areas of algebraic topology. So in principle, calculations in the equivariant world are more complicated. So maybe complicated is not a good word here. Maybe we should say rather that they are more complex. And this is due to two facts. So firstly, when we think about non-equivariant homology or homotopy or what non-equivariant whatever, everything is graded over the ring of integers. Here, we'll have bigger grading, which I will discuss in a moment, but we've already seen an example. So in C2 equivariant world, the grading is two-dimensional. Secondly, Coefficients of homologic theories have more structure. This will be discussed later, but in equivariant homotopy theory, we are taking as coefficients Mackey functors instead of just rings or groups. And of course, this complexity we will see when we start doing calculations of the homology of a point. And also, so I gave you a big picture, but now let's get back to the ground. So let's discuss why it is important just to compute this homology of a point. So first motivation, at least for me, is that point is pretty simple object, and it would be really good to know how to compute its homology. Secondly, there are two important or prominent computation techniques in equivariant homotopy theory. One is the Tate square. So this is the one which we are going to use and discuss. And the other is slice spectral sequence. So slice spectral sequence is kind of analog of Postnikov tower in equivariant homotopy theory. But in order to run the computations, we sometimes need auxiliary techniques to compute the cofibers which will be appearing in the tower. So for that matter, we are using the Tate square technique. This is one thing. So also power operations. If we are trying to compute Steenrod algebra or equivariant Steenrod algebra, or for example, start to think about Dyer-Lashev operations in the equivariant loop spaces, then we will also need to know these basic coefficients. And of course, last but not least, homology and cohomology of GCW complexes. Okay, so let's start to discuss some background. And the background will consist of C2 Mackey functors and the Bredon homology. So before going to the Bredon homology, I would like to discuss well, the coefficients of these homologic theories. So these are Mackey functors. They are, of course, defined for all finite groups. But in order to keep things simple, we'll discuss them just for C2. So C2 Mackey functor consists of 2 abelian groups. Actually, they are indexed by the orbit types of C2, but I will usually refer to them as bottom and top. And these abelian groups, so the bottom one has possibly non-trivial C2 action, and the top one has always trivial C2 action, and they are connected by 2 maps. So the one going from the bottom to the top is called the transfer, and the one going from the top to the bottom is called the restriction. So what we require from these maps is that they are both C2 equivariant, which just boils down to the following statements: that codomain of the restriction needs to be in the fixed points of the bottom abelian group, and the transfer needs to factorize through orbits of the bottom group. And the other condition is known as the Mackey formula. So if we start in our bottom group, we go via transfer, then we go down via the restriction. Then actually what we are doing is we are multiplying by the element 1 plus gamma, also known as the norm element for C2. And some examples of Mackey functors. So here, the first one is the constant Mackey functor on the integers. So the bottom and the top groups are integers with the trivial action. As usual with constant Mackey functors, we have the restriction is the identity, and then the Mackey formula is telling us that the transfer has to be multiplication by 2. The other constant, well, example of a constant Mackey functor is a constant Mackey functor on F2. So same idea here, we have F2 with, of course, trivial C2 action. We cannot have any other. the restriction is identity, and then the Mackey formula forces us to have the transfer to be 0. The very important Mackey functor is the Burnside Mackey functor. So this is the one given over here. In the bottom, it has the integers as with trivial action, but on the top it has the following ring. So I gave you here explicit formula for this ring, but actually this is the Burnside ring of C2. So do you want me to explain quickly what is Burnside ring? Yes, okay. So Burnside ring, what we are taking is isomorphism classes of orbit types of in general group G, but in our case it will be C2, and it is a ring under
Excuse me.
yes.
So do these orbits satisfy Burnside's lemma?
Well,
Orbit stabilization.
No,
I think is okay.
no, it's a different idea of Burnside.
Okay, thank you for the help, because I wouldn't know how to answer this question. Yeah, so it is a ring under the disjoint union and the Cartesian product. Okay, sorry, this is a semi-ring under these operations, and then we need to add the additive inverses. So in particular, if we have C2, then this is a ring given by two classes. We have a class of C2 mod E, and this is what I denote by omega, and we have a class of C2 divided by C2, and this is the identity of the ring. Okay, so coming back to the Burnside Mackey functor, the transfer is given by multiplication by omega, and the restriction is given as follows. We send identity to identity, and we send omega to 2. We will discuss it later, but this is very important Mackey functor because it occurs to be unit. So a category of Mackey functors has symmetric monoidal product, and the Burnside Mackey functor is a unit for the symmetric monoidal product. Okay, so the last one is just an example of Mackey functor with a non-trivial action on the bottom level. So Z twiddle is our integers where the action of C2 is given by sign. And this Mackey functor is fixed points Mackey functors of Z twiddle. So of course, fixed points of Z twiddle are 0, and we know what the restriction and transfer are. Okay, so are there any questions so far? Okay, so let me proceed to the Bredon homology. So here we start with the assumption that the G is a finite group, and how we should, well, instead of defining Bredon homology for you, I would like to give an idea how to think about it. What are the differences between the ordinary non-equivariant homology theory and what are the similarities? So definitely the similarity is that ordinary equivariant, that Bredon homology is an ordinary equivariant homology theory in the sense that it satisfies equivariant Eilenberg-Steenrod axioms. So equivariant Eilenberg-Steenrod axioms are just like normal non-equivariant Eilenberg-Steenrod axioms. We just put G wherever possible. Then the differences are that the coefficients of the Bredon homology are in the form of Mackey functors. So this is what I already said, that the coefficients of Bredon homology of ordinary homology have more structure. Well, because they are Mackey functors. And yes, and the second big difference is that the Bredon homology is graded over the ring of G representations denoted by ROG. So what ROG is? Once again, we use this idea of Grothendieck construction. So we start with ROG twiddle to be the semi-ring of isomorphism classes of real G representations. And this is semi-ring under a direct sum and the tensor product. And then, well, we do the similar thing as with a Burnside ring. So we do the Grothendieck construction on ROG twiddle. In other words, we are just adding additive inverses. So example here is that RO of CP for P prime, so CP is the cyclic group of a prime order, is just the polynomial ring on one variable divided by the polynomial x to the power P minus 1. And the generator is the generator X is the representation, the two-dimensional representation. If P is if P is odd, this is two-dimensional representation where this one where the action is given by the rotation by cosine 2 pi over P, cosine 2 pi over P, sine 2 pi over P, minus sine 2 pi over P. So in particular, arrow of C2 is graded, is two-dimensional, generated by and one-dimensional sine representation denoted by sigma. So this is a justification of the plane picture which I gave you in the beginning. Okay, coming back to the Bredon homology. So in the non-equivariant homotopy theory, stable homotopy theory, how we are thinking about general cohomology theories is we are thinking about them as spectra. So here we have similar idea. And in particular, if we have ordinary homology theory, it is represented by Eilenberg-MacLane spectrum, which is up to weak equivalence, characterized by the fact that its homotopy is concentrated in degree 0. So here we have similar idea. We also have for Bredon homology with coefficients in a Mackey functor M, we have an Eilenberg-MacLane spectrum HM, which is also characterized by the fact that its homotopy is concentrated in degree 0, but only the homotopy graded over trivial representations. So this is what usually people refer to as Z-graded part of the ROG graded gradation. Yes, because the trivial representations, n-dimensional trivial representation, just corresponds to the nth grading of non-equivariant theory. Okay, but as I showed you in the beginning, if we leave the trivial representations, then actually there might and they occur non-trivial spots. And how are Eilenberg-MacLane spectra and its homotopy connected to the homology of a point? Well, by this formula, actually, it is just the same thing. And this 5-pointed star over here denotes the ROG gradation. In other words, pi g in the dimension in the degree v. These are G homotopy classes of maps from SV to HM. And I should also say what is SV. SV, so V is a representation and SV is just 1-point compactification of V. Okay. So our goal in this talk, and now I will rephrase it, will compute the homotopy groups, ROG graded homotopy groups of C2 equivariant Eilenberg-MacLane spectra, which I will denote as by this thing.
Igor,
Yes.
you pointed out that the two main differences between this equivariant world and the classical non-equivariant world is that the grading is over ROG and the coefficients are now Mackey functors. In a heuristic, cartoonish way, would you say that most of the difficulty comes from one of those two? I would be guessing the ROG grading. Is that generally what happens?
Yes. So firstly, these things are closely connected because so I think this was Peter May who showed that okay, Bredon defined this kind of cohomology only for Z grading. Then I suppose it was Illman who defined the homology. And then Peter May showed that it can be extended to ROG grading if the coefficients are of the form of Mackey functor. Oh, because usually if we define the Bredon cohomology, we are just taking we think about the Mackey functor, but we are just taking restrictions. And if we discuss the homology, we are just taking transfers. So firstly, these two things are actually very closely connected. And the answer, I think, is yes, this is the crucial problem.
Okay, and if we try to understand the simpler Mackey functors, I would guess that the example you mentioned of trivial, sort of constant Mackey functors is the simplest kind, right?
Yes.
And remind me, does that work for, I can take any abelian group and jazz it up to a constant Mackey functor with value that abelian group, right? And then the restriction maps are all identities, and the Mackey formula forces unique transfer maps, right?
Yes.
Okay, so given, right, there's a unique way of writing all the transfer maps to make that into a Mackey functor.
Yes.
Okay, and is that also true for any finite group, or is there something special about cyclic groups? The fact that any abelian group can be jazzed up to a constant Mackey functor?
No. So this you can do for every group.
Okay, that's a general fact.
Every group, yes. Then you the constant Mackey functor is defined as follows. You are taking the abelian group. It is an entry of the Mackey functor on all orbits, and all the restrictions are identities. Then the Mackey formula will tell you what are the transfers.
I see. That's true for any finite group G.
Yes.
Great. Thank you.
Okay. Any other questions? Okay. Yes. So, okay, I established our goal for this talk. Here I have also a small cheat sheet over C2. So this cheat sheet is supposed to tell us how this homotopy is connected to homology and cohomology of some spaces. So here I forgot to write this, that A and B are supposed to be greater or equal than 0. And then the homotopy in the degree B sigma minus A is, well, just by definition, this is the same thing as a C2 equivariant homotopy classes of maps from the sphere of B sigma minus A, representation sphere. So this is the same thing as the cohomology, the eighth Bredon cohomology of the sphere B sigma with coefficients in M. And similarly, the A minus B sigma homotopy of HA, this is the eighth homology of S of B sigma. Okay, now let's discuss the coefficients of Eilenberg-MacLane spectra over C2. So, okay, probably what I will be saying generalizes also to all finite groups, but I specialize here to the cyclic group of order 2. So this coefficient has 3 levels of structure. So firstly, it is an ROC2 graded abelian group. So this is kind of the basic level of the structure. Then this is the thing which I already mentioned. So Mackey functors, the category of Mackey functors has a symmetric monoidal product called the box product. And the Burnside Mackey functor is the unit for this symmetric monoidal product. Therefore, every Mackey functor is a module over the Burnside Mackey functor. And given this, coefficients of all Mackey functors are module over the coefficients of the Eilenberg-MacLane spectrum associated to the Burnside Mackey functor. And the third possible layer of the structure is that if our Mackey functor occurs to be a green functor, so this is a ring Mackey functor with respect to the box product, then also the coefficients will have ROC2 graded ring structure. Okay, so before we start to do...
Sorry, Igor, just for
Yes?
intuition, that's just the analog of saying that, let's see, wait, was that homology or cohomology? I'm trying to look for a classical analog, and I'm thinking of, well, okay, if I want the cohomology ring of a space, I do want the coefficients themselves to be a ring. It feels like there's something going on there. You're saying that if the coefficients have a multiplicative structure, then I get a ring structure on what exactly?
So just think about it stably. So if you take the coefficients of some, well, Eilenberg-MacLane spectrum, okay, this is pretty easy. Anyway, no, so
you're saying, yeah, you want this classical Eilenberg-MacLane spectrum HR to itself be a ring spectrum in some appropriate sense.
Yes, exactly.
I see. That's what's going on here.
Yes, but okay, if we take this analogy of being, well, okay, so this should be cohomology, you're right. So firstly, cohomology is, of course, just graded abelian group. Secondly, cohomology is, well, so this says nothing, but this is a Z module, right? And thirdly, if, yes, we are right, if the coefficients are ring, then the cohomology becomes also a ring.
Right, and HR becomes a ring spectrum.
Yes, exactly.
That's okay. Yeah, that makes sense. Thanks.
Okay, so some history over here. I will just go over it quickly. So the first occurrence of these computations are in a legendary unpublished work of Stong. Yes, so the first one who computed the coefficients of the sum Mackey functor and published it was Lewis in 1988, and this was the Burnside Mackey functor over C2. We are all time over C2. And then Fairland in 1999 and Fairland Lewis in 2004, they gave ROC2 graded abelian structure of all Mackey functors, coefficients of all Mackey functors, and also they gave the structure of the module over the coefficients of Burnside Mackey functor. Other computations are by Caruso in 1991, so he computed the coefficients of IHF2, and Dagger in 2005, he computed the coefficients of IHZ. Okay, now let's proceed to some actual computations. So the computations of the coefficients of these Eilenberg-MacLane spectra have two easy parts. The first one is the horizontal line. So this one we already know. It is very easy. It is concentrated in degree 0, and in degree 0, it is just the top level of our Mackey functor. So this is easy. Then it occurs that the vertical line is also very simple. So vertical line corresponds to the multiplicities of the sign representation. And how it goes. So firstly, we start with the inclusion of S0 into a sigma. So maybe let me draw some pictures if I find a space. So this is a 0. We have a point and a base point. And how does a sigma looks like? We have a point, we have two fixed points, and we have two orbits which are interchanged by the axiom. Right, so we are just taking them. Okay, maybe this is a good point also to say how a sigma is produced. So we are taking the sign representation. So this is just a real line where C2 acts by the sign. And then we are taking the 1-point compactification. So we are closing the whole line to the circle, and we take the infinity as a base point. So this is how S sigma, where it comes from. And this map is very simple. Of course, we send fixed points to fixed points. And yes, this inclusion gives us a homotopy class in the degree minus sigma in the homotopy of the sphere spectrum, because this is the same thing as zeroth homotopy group of a sigma. So these are just C2 equivariant homotopy classes of maps from S0 to S sigma. So let's call this class A. And for any C2 spectrum X, we can define the multiplication by A. So this is just the map. We just smash X with this inclusion S0 to S sigma. And actually, we can describe this multiplication by using the following homotopy cofiber sequence. So once again, let me draw some pictures over here. So C2 plus, well, this is free orbit of C2 with disjoint base point.
Excuse me.
Yes.
Sorry. This might be a naive question. So in the middle of your page,
Yes.
in the square brackets, is that a representable functor category? You've got
So
in square brackets dash comma HM.
Over this one, right?
Yeah.
Representable functor. Okay, what do you mean here?
Well, I'm used to, okay, well, on the previous slide, you've got pi 1 or pi 0. You've got the little pi
Yes.
0. So that's a functor.
Yes.
Right? And
Yes.
I believe it's equivalent to a similar object or functor, sorry, on the previous slide. So this is all morphisms from S0 to S. Well, okay, that's my question
sigma?
is about the thing in the big box. Yeah.
Yeah, I mean, those are the maps in the homotopy category of C2 equivariant spectra, right? It's the
Yes.
Okay.
So we can view that functor hom into HM C2 equivariant maps as being, let's see, going from the homotopy category of C2 equivariant spectra into
abelian groups.
Just a abelian group a priori. Maybe there's some extra structure there, but that is what it is. And it is well, that one on the next slide is contravariant, right?
Yes. So, I mean, so it is representable, but it is kind of trivially representable.
It's also
right?
specifically represented. So
right. Right.
Yes.
I already know what it is. Yeah. Yeah.
Thank you.
Okay. Okay. So coming back to my pictures. So C2 plus is the free C2 orbit with the disjoint base point. Then it is sent to S0 as follows. Base point is going to the base point, and the free orbit is going to the other point of S0. And then the homotopy cofiber of this map is just S sigma. Now, if we apply this functor to the cofiber sequence, which is in the box, what we get is the following sequence. So we start with HM sigma, which goes to HM0, and this goes to the homotopy classes, C2 homotopy classes of maps from C2 plus to HM. But we actually know a lot about this sequence. So firstly, just by the dimension axiom, we know that this guy over here is the top level of our Mackey functor. And also we know that the guy on the left-hand side, well, this is, yeah, okay, I already wrote it. I already, yes, this is actually pi0 of the restriction of from the C2 to E of the Eilenberg-MacLane spectrum, but the restriction of Eilenberg-MacLane spectrum is Eilenberg-MacLane spectrum itself. So this is the same thing as pi0 of h of, okay, I need to write M C2 mod E. So this is now a non-equivariant Eilenberg-MacLane spectrum, and we know what is pi0 of a non-equivariant Eilenberg-MacLane spectrum. Also, if we extend this sequence to the right, we see that we'll get 0 over here. So this tells us everything about what is HM sigma. And we get that HM sigma is isomorphic to the kernel of the restriction of in our Mackey functor. And by similar calculations, what we get is that if we think about the vertical line, so everything which is above 0 are kernels of the restriction. Everything which is below 0 are co-kernels of the transfer. And in the 0 spot, we have our top level of our Mackey functor. And this actually can be extended. So if we have a multiplication from by A from x plus y sigma to x plus y minus 1 sigma, this can be described as given here. So it is a monomorphism if x minus 1 is equal to I, epimorphism if x is equal to minus y, and isomorphism otherwise. So pictures. Okay. So if we think about the plane, what is A doing? A is just going one spot down. Multiplication by A is just going one spot down. And this statement is telling us that multiplication by A is an isomorphism unless we either hit or start from the anti-diagonal. Okay. So this was the kind of the easier part of the computations, and this is how it looks like. So the vertical line, as I said, we have in the 0 spot the top level of our Mackey functor. Below 0, we have the co-kernel of the transfer, and above we have the kernel of the restriction. Okay, so now let's go to the harder stuff. So the Tate square. This is the technique which we are going to use. So let's start now with the compact Lie group, and let EG be, as usual, a free contractible G space. And we define the following cofiber sequence. So we send EG plus to as 0, base point to the base point, everything else to the other point of a 0, and denote the cofiber as EG twiddle. And this cofiber sequence is known as the isotropy separation sequence. Now, how we construct the Tate square? So firstly, let's apply the function spectrum from 2x to the first map. So what we get is the following thing. We have a map, we'll call it epsilon, from f of s0 to x, which is actually isomorphic to x. And this map goes to the function spectrum from EG plus to x. This is just induced by the first map in the isotropy separation sequence. And now the Tate square or the Tate diagram just comes by smashing the epsilon with the isotropy separation sequence. So what we see in the top is x smashed with the isotropy separation sequence, and in the bottom, at the bottom we have f, the function spectrum from EG plus to x smashed with the isotropy separation sequence and connected by epsilon and respective smashes. However, we know one more thing about this diagram. So this map, the left-hand side vertical map occurs to be a G equivalence. And so we get that the square over here is actually a homotopy pullback. Now, there is a plenty of letters in this diagram, so let's give some names over here. And the names are as follows. So X subscript H, this is EG plus smash X, and this is called the free G spectrum associated to X. Then X superscript H is the actor which we already know. So this is the function spectrum from EG plus to X. And this is called the Borel completion of X. Then X superscript phi is EG twiddle smashed with X, and this is called the singular G spectrum associated to X. And X superscript T is EG twiddle smashed with the function spectrum from EG plus to X, aka X superscript H. And this one is called the Tate spectrum of X. So after renaming the entries, we get this diagram over here. And this one is called the Tate diagram. And in particular, the right-hand side square in here is called the Tate square. Yes, so just a comment, which I'm not really fluent in, but the Tate square is kind of in the general framework of fracture square. So if you know what a chromatic fracture square is, then these ideas are fairly similar.
Sorry, Igor.
Yes.
Just for reference purposes, your function spectrum from EG plus into X is what some references call the homotopy fixed points, right? Your upper H, or is there a difference there?
Nearly. So homotopy fixed points would be after you've taken the fixed points of this spectrum.
Oh, right. You're not taking the fixed points. It's actually just the function spectrum from EG plus.
Yes, not yet.
I see.
And
okay. And likewise with the smashing with EG plus, you're not taking orbits, so it's not the homotopy orbits. Okay, it's closely related, but I see. Yep, thanks.
Yes, and actually in the main reference for the Tate square, so the Greenlees May generalized Tate cohomology, they have different name for F EG plus to X, and actually I don't remember the name at the moment, but the Borel completion is kind of well established right now. And the Tate square has also very nice property that if X is a ring spectrum, then the Tate square is a homotopy pullback of ring G spectra. Same may be told if X is a module over some other spectrum, then the Tate square will be homotopy pullback of module spectra. Okay, so let me, because actually it occurs that I have 5 minutes left, right?
Plus epsilon.
Second?
Plus epsilon.
Plus epsilon. Okay,
yes.
I will. Okay, very good. So let me give you the idea how the strategy of calculations look like. So we start well with a C2 Mackey functor. Here we have a Tate square diagram just for the reference. So we start with computing the bottom sequence firstly, and this we can do well. Now we are taking the fixed points because yes, the coefficients of the Borel completion are the same thing as C2 equivariant homotopy groups of H of the Borel completion. Yep. Okay, I messed a little bit. The point is that now we are having fixed points here. So these are homotopy fixed points. And we can compute these two objects by respectively homotopy fixed point and homotopy orbit spectral sequences. So we have spectral sequences for the computations. Well, so more or less, usually we can calculate something. Then, so we have computed these two guys. And then we derive, the second step is the derivation of the coefficients of the Tate spectrum. And we have two techniques over here. Firstly, we can derive it just from the map. So we know that the Tate spectrum is a cofiber of this map. And we know the formula for this map. However, we can also think about it as just inversion of A in the coefficients of the Borel completion. And this is just because the Tate the Tate spectrum is defined as EC twiddle smashed with the Borel completion. And we have nice model of EC twiddle. So this is the colimit over I of the representation spheres. So then the coefficients of the Tate spectrum are the colimit of this sequence. So a colimit of the consecutive multiplication by A, which is just localization in A. So we have computed the bottom sequence in our Tate diagram. So now how we infer the coefficients of the singular spectrum. So by the following lemma, if X is a C2 spectrum such that it is non-equivariantly connective, then if the map, so this is map epsilon, after taking fixed points, is a connective cover, then so is the map from C2 fixed points of the singular spectrum to the C2 fixed points of the Tate spectrum. And finally, we can compute the coefficients of HM. So yes, here are references. The main one is Greenlees May generalized Tate cohomology. This is where they derive the Tate square and Tate diagram. And the reference where John actually used the technique which I just described is the 4 approaches to cohomology theories with reality. And he used this technique to compute the coefficients of HZ and also the K theory with reality. Okay, so how this procedure looks like, very kind of algorithmically. So we start with the step 1 over here. Then step 2 was to derive the Tate spectrum, coefficients of the Tate spectrum, then derive the coefficients of the singular spectrum. Then the grand finale is the coefficients of our Eilenberg-MacLane spectrum. And here, well, after you, of course, have some practice, it occurs that this is an algorithmic approach kind of with really easy steps. So I think I will do the toy case and then I will stop. So our toy case will be the spectrum which I discussed in the beginning. So this is Eilenberg-MacLane spectrum associated to the constant F2 Mackey functor. So the step 1 will be, as you remember, computing these 2 guys in the bottom sequence. And for this, we use the homotopy fixed point spectral sequence and homotopy orbit spectral sequence. These spectral sequences can be made into be 3 graded so that we actually compute arrow G graded, arrow C2 graded homotopy groups of these 2 spectra. And important part for us now is that on the E2 page, what you have is just the group cohomology and group homology of C2. So this is fairly well understood. I mean the group cohomology and homology of C2. And also, if our spectrum is F2, then the coefficients, if in this group homology and cohomology, will just become the F2. So the field on with 2 elements. So it occurs that we have the following pictures. These are arrow G, arrow C2 graded coefficients of the Borel completion and the free spectrum. Now, so this was the first step. The second step was to compute the coefficients of the Tate spectrum. So here the coefficients are also really easy because we have a plane full of dots. Yes, how we can see this, for example, if we take the coefficients of the Borel completion and we invert the class A. So remember the class A was going down. Now, if we invert this class, then we will fill the plane with dots. And by the connective cover lemma, we also get the coefficients of the singular spectrum. So the connective cover lemma in this case is telling us just that we are cutting off everything which has trivial degree lower than 0. So finally, this is the diagram which we are supposed to compute. And now the grand finale is that the answer is as expected. So this is what I gave you in the beginning. Yes, maybe because okay, maybe I will give you also the general answer. So if we take any Mackey functor, then this picture depicts the full ROG graded abelian structure, abelian group structure of its coefficients. And a couple of important points here are, I know that there are plenty of information on this picture, but important points are that if we are on the right half plane above the anti-diagonal, all groups are 0. Same if we are on the left half plane and below the anti-diagonal. Secondly, these are this is the vertical line which we computed as an easy step. So this corresponds to multiplicities of the sign representation. And also on this line, we have modules, we have submodules of the top level of our Mackey functor, subgroups. In the dimension, in the trivial degree 1 and trivial degree -1, we have subgroups or subquotients of the bottom level of our Mackey functor. And these cones over here depends on respectively cohomology and homology of a group with coefficients in the bottom level of our Mackey functor. Okay, so I got somewhere, so I think this is a good place to stop. So thank you very much.
All right, let's unmute ourselves and thank Igor for a very nice talk.
Okay, thank you.
Are there any questions?
So when I was listening to this, I was wondering about bigger groups. What changes if the order of the group or the number of real orthogonal representations is more than 2?
Yes.
What does the picture start to look like?
So it sometimes is not so complicated. Sometimes it is quite complicated. So this technique should also work for all cyclic group of prime order. There is nothing kind of special about C2, just that it has 2 irreducible representations. What then we are working with. This was one point which I wanted to say, but I didn't get to it, that we are working on extension of this project, of these computations to the cyclic 2 groups.
Mm-hmm.
And here the important point and the thing which makes these computations possible, where I don't know, possible is a good word, but feasible, is that C2 case and CP case, cyclic 2 or P groups have linear order on subgroups. Yeah. So then the Mackey functor is rather easy because you will just have kind of a tower Mackey functor, and everything is kind of described by going just from one subgroup to the subgroup of order with 2 times order of the subgroup. Yeah. So you have very simple steps. But for example, if you think about something about non-cyclic group, like the Klein 4 group, then it occurs that it is quite hard. And I don't know whether the computations were done so far.
Yeah.
So in general, it is quite surprising because this was my point in the beginning, because these objects should be easy to compute. I mean, the homology of a point should be easy to compute, but it occurs that it is not the case.
Yeah.
So there are only few groups for which the computations are done. I think that for the quaternion groups, for the quaternions, this is done. For the dihedral group of order 8, this is done. Yes, and I don't know how about other groups. So yes, maybe I would like to just say two more things. So it is not the problem with the number of irreducible representations. Rather, the problem is with the order on the subgroups. So this is one point, and the second point is that the Tate square technique, that this Tate diagram technique, it works, as you've seen, very nicely for C2 or CP, but if you start to do these computations by the Tate square for cyclic 2 groups with order bigger than 2, let's say 4, then you start to have plenty of relations which you need to do big bookkeeping. So then it's not, maybe it's not complicated, but rather complex, therefore complicated.
Yeah, it could have a sort of a series of gradings that one must have to account for, right?
Yes. Yes, but my point here was that when you start, so you have two parts of this coefficients. So this part is usually very simple. So over C2 case, this is usually truncated polynomial ring. But then you want to compute also this part. And this cone is a module over the cone. This positive cone is a module over the negative cone. And then if you want to actually describe the structure of this module, then you have plenty of relations which you need to keep track of. And this is the complex task here. Yes. So I think this is the answer.
Okay, thank you.
Thank you.
I have a question as well. We ran a learning seminar on spectral sequences last semester. So that's quite exciting to see those homotopy fixed point spectral sequences showing up in homotopy orbit spectral sequences. You mentioned that they're trigraded. Just to clarify, so each page is trigraded in the sense that it has a homological degree, which is Z graded, and some internal degree that's ROC2 graded. Am I following correctly?
So they are trigraded, at least in this case, in the following sense. So there exists, okay. So for every value of Y, we have a spectral sequence. No, okay, rather I would like to say the following thing. So for every value of, okay, maybe, sorry. So how we are thinking about this trigraded spectral sequences is that for every value of Y, you have just one sheet of the spectral sequence. So then all of the differentials, everything, all of the differential leaves only on the single layer corresponding to one value of Y.
Oh yeah, I was wondering about that. So the tri degree of the differential, it's 0 in the direction of the sign representation. It doesn't change that weight or whatever it's called.
Yes. The only thing why you think about it as a trigraded spectral sequence is that you might have well, it is trigraded multiplicative spectral sequence. So if you have a class, I don't know, in degree 1 minus 1 sigma, let's say, then its square will be in degree 2 minus 2 sigma, 2 sigma.
And you can use that to your advantage in the calculations then.
Yes.
Yeah.
Mhm.
Right.
I mean, advantage in the sense that in this way, we are actually getting the whole coefficients of the border completion and the free spectrum, at once. So we are not computing all rows separately, but rather we are we are getting everything at once.
Right, and they are multiplicative spectral sequences. They satisfy the Leibniz rule. Yeah, got it.
Yep.
And also, one thing we learned in the seminar is that we should be wary of spectral sequences not being algorithmic in general. So were you saying algorithmic in a technical sense, that those happen to not have any kind of extension problems, or was it more of
Yes.
a algorithmic in quotation marks?
Okay, I see the point. It was algorithmic. I think in quotation marks, but
Okay, so something we can compute.
No, so here there wasn't any quotation marks, because for every value of y, the spectral sequence collapses on the second page. So, and this happens for every Mackey functor. And well, this just becomes from, it comes from this formula over here. So what we are having as a coefficients are the homotopy groups of the function spectrum from Sy to X. Okay, whatever it means, it is either homology or cohomology of a sphere and reduced. So homology or cohomology of a sphere is non-zero only in 1 degree, right? So then it is non-zero. So fix y, it is non-zero for only one value of q. So then you have only one row on the second page.
Oh, so there's no room for differentials. It collapses at E2.
Yeah, it collapses on the second page.
I see. But what about patching the answer from the abutment? Are there some issues there?
No, so both spectral sequences are, I think, strongly convergent in this case.
Right. Great. Yeah. So it is actually an algorithmic calculation. That's very satisfying.
Yes, in this case, yes.
Right. Okay. Any more questions for Igor? If not, let's thank our speaker again.
So thank you very much for having me here.
And thank you all for coming. Take care, everyone.